Hello, testing, testing. Can you hear my voice? Hello, hello,
not
hello, hello, hello. Can you hear my voice?
Yes, I can hear your voice.
Thank you. No one can hear my voice. Okay. Okay. Assalamualaikum warahmatullahi taala wabarakatuh, and a very good evening, ladies and gentlemen. We are about to begin. I would like to thank you for your time, cooperation to avoid any virtual difficulties during the live broadcast. If you have any questions, the question response personnel are ready to attend you at the session. We will start at 3:35, around 5 minutes from now. For evaluator, please check your private message for evaluation form link. Okay, Assalamualaikum warahmatullahi taala wabarakatuh, and very good evening, ladies and gentlemen. Welcome to the first Malaysia International Conference on Nanotechnology and Catalysis MICNC 2021. We are now in the session Advanced Nanomaterial for Catalysis. My name is Muhammad Hafiz bin Ahmad from Nanotechnology and Catalysis Research Center, University Malaya. I will be the session chair today, together with the session moderator, Ms. Shabila Sazli and Mrs. Nurul Fatimah Basir. Okay. I invite all the invited speaker and presenter to request to share audio and video now. Ladies and gentlemen, oral presentation will be evaluated for the award under two categories. Best Session Presenter that will receive the certificate for Best Presenter, and I will announce at the end of this session. Best Presenter Award that offer prize money from 500 to 1000 ringgit, trophy and award certificate. This will be announced during the closing ceremony. I would like to seek your kind cooperation to mute your mic if you're not presenting and to avoid any kind of virtual disturbance as possible. For those who intend to ask questions to presenter, you can channel your question in chat box. I will read it after every presentation. You can also request to share your audio and virtual to ask your question in live mode. Presenters are given 15 minutes for presentation and 5 minutes for Q&A session, whereas invited speakers are given 25 minutes for presentation and 5 minutes Q&A. I will remind the presenter at the end to the end the presentation. For oral presenter, 5 minutes before to both presenter 5 minutes before the presentation session end. I will stop the presentation session when the session has exceeded the 5 minutes allowed. Before we start this parallel session, I would appreciate if everybody can turn on the camera for photo session. Okay, okay, 1, 2, 3, smile. Okay, okay, we have another 2 minutes before we start our first presenter. Oh, okay, okay. Mrs. Nur Azima, can you please turn on your camera, and Dr. Muhammad Adil, because we want to take a photo again. Dr. Muhammad Adil. Okay. Okay, smile. 1, 2, 3. Okay. Okay. Without further delay, you will be hearing a presentation from Dr. Muhammad Adil Mansur and his presentation entitled Fabrication of Bimetallic Chromium 3 Oxide, Manganese 3 Oxide, Thin Film for Photocatalytic Water Oxidation. Please welcome. Excuse me for IT committee. There is no voice for this.
Shabila? No voice.
Sorry. Sorry.
Bismillahirrahmanirrahim. I'm Dr. Muhammad Adil Mansoor, Associate Professor in National University of Sciences and Technology, Islamabad, Pakistan. First of all, I am very grateful to the organizing committee for this kind invitation and acceptance of my paper to present at this platform. Without any further delay, I would like to share the topic I have to discuss. It's basically the aerosol-assisted fissile fabrication of bimetallic electrocatalytic chromium oxide, manganese oxide composite thin films for water splitting. Prior going to the detail of my research findings, I would like to share some background, especially for the students and PhD scholars who are highly interested to pursue their future research in this field. Basically, the whole world is facing the energy crisis issues and global warming problems. These are the biggest challenges in the current era. Therefore, we are looking for some alternate sources of energy. Already, the existing energy sources like tidal power, windmills, sea waves, and geothermals are there, but they are either area and weather dependent, or they have the problem of energy storage issues. Therefore, we are trying to utilize sunlight to produce hydrogen as a renewable energy source. So from where we got the idea of utilizing hydrogen energy, it is basically the photosynthesis. We find that the photosynthesis in plant, in which the plant cells, the chlorophyll of plant absorbs the sunlight and convert carbon dioxide and water into glucose. So this was the idea, that was the basic pinpoint to generate photos electrodes in the laboratory. So that's why we were trying to mimic a plant leaf. So how we can mimic a plant leaf? It's a very simple. Just we have to fabricate electrode material, the photoactive material. Once the light falls on this photoelectrode or photoactive materials, what happens? The electrons from its valence shell jumps to the conduction band. And this electron via external circuit moves towards the counter electrode that may be of platinum metal. The platinum wire can act as electrode, the counter electrode. The electrons that are produced during the excitation will move towards the counter electrode. So holes are generated on this material. So these holes will interact with water. And what happens? The holes separate the oxygen from the protons. So oxygen as a gas evolved here. These protons will move toward the counter electrode via electrolyte. Once the hydrogen reaches the counter electrode, it absorbs electron, captures the electron, and the reduction of proton takes place to produce the hydrogen gas. So overall reaction is that the light is utilized in the presence of a catalyst, and water is split into hydrogen and oxygen. So why we are focusing to produce hydrogen via sunlight? Why we are going to prepare the photocatalyst? In fact, if we are going to prepare to produce the hydrogen from water by thermochemical process or electrolytic process, we have to provide high energy. The input is high as compared to the output. So low, it is cost ineffective. In other words, you can say that it is cost ineffective and is useless. At the same time, if you go for the production of hydrogen from hydrocarbons, then the combustion of hydrocarbon in the limited oxygen produces the hydrogen. But again, the problem is that the byproduct is carbon monoxide or carbon dioxide that are again the greenhouse gases and may cause further global warming. Therefore, we are looking to the alternate method where we just produce the hydrogen by the water splitting without providing extra energy in the form of potentials, electric potential or thermal heat. So that's why we are trying to produce hydrogen via photocatalytic materials. So what are the requirements for the material to be a photoactive material or photoactive or photoelectrode? It must be cost effective. It must be stable towards the photocorrosion. It means it shouldn't be starting depleting. The band gap should be narrow. For the water, normally the band gap for the water splitting, we need the energy of 1.23 electron volt. In addition to that, with our potential, it is normally 1.6 electron volt. And it is observed that if the energy is equivalent to 1.6 to 2.2 electron volt, and in other words, the energy of band gap is in the range of 1.6 electron volt to 2.2 electron volt, then they can be efficient material for water splitting. At the same time, absorption coefficient must be large. It must absorb most of the light, especially in the visible range, and least electronic recombination. Electrons that are excited must move to the external circuit rather than they are again recombining to the holes. So these, keeping in mind, several materials have been prepared previously, in which the titanium was the first material that was studied by Fujishima. However, it was photoactive material, but the band gap is very high. It works in UV, in ultraviolet range of the radiation. So there are also other zinc oxide and iron oxide, tungsten oxides have also been studied. But the problem is that these materials either have a high band gap or they have low band gap, but their stability is not good. They may undergo the photocorrosion. So what we can do the band gap engineering. We can select those materials having high band gap, and we incorporate another material as a composite or as a solid solution that can help to reduce its band gap by synergistic effect or by making a solid solution in that in the lattice of the existing material. So what we can do, the band gap engineering, several papers already I have published regarding manganese zinc oxide in solar energy materials. This one is the zinc cadmium oxide in Journal of Material Chemistry A, manganese, titanium, cadmium, manganese, etc. Several attempts have been done, and we have been succeeded in engineering the band gap of the zinc oxide and titanium oxide. Apart from the band gap, bandage is also important, and it confirms whether the material is going to be used as a cathode. If it is working, its band edge is close to the reduction potential of water, then it will act as a cathode. And if its band edge is close to the oxidation of water, it will act as an anodic material. And most of the material we have synthesized are the photoanodic materials. Similarly, in the present study, we also have prepared a photoanodic material. Regarding the synthesis, there are several techniques. Without explaining the pros and cons of different techniques because of the limited time, I will directly focus on the aerosol-assisted chemical vapor deposition. So aerosol-assisted chemical vapor deposition, we need a just precursor that is soluble in organic solvent. Once it is soluble in organic solvent, we place the flask on the ultrasonic piezo-modulator. It agitates the solution solvent containing our targeted precursor. Like in present study, we have to prepare chromium oxide and manganese oxide. The precursors are chromium acetate and manganese acetate. So chromium acetate and manganese acetates are dissolved here, agitated. The aerosols are produced. These aerosols are pushed by the gas. We are supplying the inert gas like argon, and if we need oxidation of the material, we may use oxygen or air. But here in this case, we utilize the argon as a carrier gas, which that pushes the aerosols into the tube furnace. Once the aerosols have been reached in tube furnace, what happens? The high temperature above 400 degrees centigrade decompose the precursor into oxides. These oxides are settled down on the substrate like FTO glass, ITO glass, or any other metal can be used as a substrate. These aerosols are just decomposed into metal oxide. Metal oxide is deposited on these thin films, and the rest of volatile material is escaped from this exit. This is a very simple technique, and this technique was utilized for the preparation of chromium oxide, manganese oxide composite thin film. Well, the current material, the chromium and manganese composite oxide thin films were prepared from the chromium acetate and manganese acetate solution was dissolved in THF, and the AACVD was performed at 400 degrees centigrade, and the volatiles were escaped. So after the films were generated, like here I have shown, these films are basically the active coated with our material chromium manganese oxide. These were then subjected to the characterization, and the characterization, the very first technique was the XRD. The XRD confirms the manganese oxide and chromium oxide, which are very well in a good match with the standard ICTD card numbers. These are available here, and this confirms that this is the impurity-free chromium manganese oxide thin film. Similarly, the surface morphology was studied by FPSCM, and it shows that the manganese oxides are producing the nano rods. The rods are here, which are decorated with the cubes of chromium oxide, and they are in well connection with each other, and thus producing a synergistic effect. And this synergistic effect leads to a low band gap of the chromium manganese oxide and manganese oxide composite thin film. At the same time, if we see, here are the pores which are clearly visible. This material is highly porous. The porosity is very effective, highly effective for the electrocatalytic activity, as maximum surface area is provided by the films to the electrolyte, and there is better electrolyte electrode interaction is there. Further elemental composition was performed. This elemental composition confirms that the chromium and manganese are present in 1:3, and here the distribution is uniform. This mapping shows the uniform distribution of chromium and manganese, and uniform distribution confirms the better interaction between the two composite materials. The band gap of the thin films were confirmed from the optical band gap, where we plot the top plot. The top plot of the direct band gap shows the band gap is approximately 2.1 electron volt, 2.08 electron volt, which is very good for the water oxidation. And therefore, the photoelectrochemical studies were performed. This is the linear scale scan voltammetry. In the absence of light, there is no current at all. However, in the presence of light, we see that there is a start of oxidation of water, and the maximum oxidation is observed at 0.3 volt versus SCE, the standard electrode. So here it is the maximum, and then there is a decrease. After 0.8, it shows again this peak is because of the electrocatalytic oxidation, not photoelectrocatalytic. However, the photoelectrocatalytic oxidation is observed maximum at this point. Further, at the 0 volt, the chronoamperometric response was confirmed by chopping in the presence of light and in the absence of light, and it shows that it is highly active even at 0 volt. Here we can see that even at 0 volt there is a difference in light and dark current, and which is again confirmed by the chronoamperometric studies. Further, the chronoamperometric studies was performed for 500 seconds to confirm the stability of material, and it was found that the material is highly stable for the water splitting even at 0 volt, and there is no such decay in the current density. At the end, we also confirmed, we can say that we supported our photoelectrochemical studies by impedance studies, and impedance studies that shows that the charge transfer resistance, here we can see that the charge transfer resistance under dark was 522 ohms, which was reduced to 395 ohms upon elimination. This shows that the charge transfer process increases and the resistance of material decreases because of the maximum electron flow under elimination. Further, in future, we are looking for the hybrid materials. We will try to prepare the films similarly by the ASCVD method, and we will drop cast our organometallic halide. And this will produce a hybrid material containing the two layers, the one layer of mixed metal oxide from ASCVD and second from the organometal halides by drop casting. And we will further study how we can improve the photo-oxidation of water and its efficiency under illumination. There are several projects I have performed, and currently I am working on HEC project as a PI since January 2001. This is regarding the metal decorated high surface area porous sodium aluminosilicates. This is basically for the hydrogen adsorption. Most of the previous work was focused on hydrogen production. Now we are currently also working on hydrogen synthesis of materials for hydrogen capturing. There are several other projects that I have completed in University of Malaya, and you can go to my Google Scholar. Here it is. You can search Muhammad Abdul Mansoor, NUST, National University of Sciences and Technology, and you can find my link. And it will be a pleasure to have a collaboration with all of you. Thank you very much. I would like to acknowledge my university, NUST, Islamabad, my alma mater, University of Malaya, HEC, NRPU grant for funding my research project. And at the end, I would like to acknowledge my whole team for this project, Amy Mansoor, myself, Dr. Khatija, Dr. Noor, and Dr. Nashrul, and Dr. Zahrine. Thank you very much for all of you, and thank you for patience. Please ask questions if there is any query. Thank you very much.
Thank you. Thank you very much, Dr. Muhammad Adil Mansoor, for addressing this interesting topic.
Assalamualaikum and very good afternoon. My name is Nurul Fatimah.
Ladies and gentlemen, now we come to Q&A session. Okay, for the first question from Ishraf Aznam. Dear Dr. Muhammad Adil, if your suggested material can be commercialized, how is the feasibility for AACD technique to be scaled up for mass manufacturing, especially in terms of cost perspective?
Yes, Israf, thank you very much. That was very interesting question. In fact, basically the AACVD is a very simple technique, and you have to purchase just a furnace that is not more than 8,000 ringgit, and the humidifier. The total cost for this material, this equipment, is not more than 9,000 ringgit, right? And this one can be utilized in a laboratory. However, if you want to commercialize and if you want to use this method in industries, it's very simple. You have to just purchase a large scale tube furnace, and then you can produce the aerosols, and the aerosols are very lighter in weight and can be pushed into the tube furnace by any mean. By you can utilize the argon gas, you can utilize the air, you can use, there is no issue, and it can be commercialized. Yes, it is very easy, and most of the industries are also utilizing the AACVD techniques for the production of thin films.
Okay, for the next question from Nur Azimah Abdul Samad. Dr. Adil, thank you for your interesting presentation. I have question on what type of nanostructure have you produced? Are you coat it on top of FTO or ITO glass, or your material is thin film itself? Thank you.
Yes, thank you. Thank you. Are of different variety. Nanostructures depends on the temperature we are utilizing. It depends on the precursor we are utilizing. It also, because there are two types of reactions taking place within the reaction or heterogeneous reaction. So homogeneous reaction are basically taking place first and then deposit on the thin films, and we are just using our substrate either FTO or ITO. The aerosols move into the tube furnace, they just get contact in the with the substrate, and then they decompose into the metal oxide. So therefore, depending upon this homogeneous and heterogeneous reaction, we can find different types of nanomaterials. They can be rod-likes, they can be cubes, and they can be sometimes of irregular shapes. This is not we cannot control.
Sorry, maybe Dr. Adil has a problem with his internet connection. Okay, for those who has any question for Dr. Adil, may privately message to him. Okay, now we are moving along to our next presenter. Please welcome
Sorry for the interruption.
Oh,
I
okay.
think it was disconnected. Am I audible?
Uh, yeah, it's okay. You can finish.
Hello?
Okay. Hello. You can finish your answer.
Am I audible?
Yes.
Yes, doctor.
Uh, okay. It's okay, Dr. Adil. Okay, we have to move to the next presenter. For those who has any question, may directly message to Dr. Adil. Okay. Now we are moving to our next presenter. Please welcome Madam Nur Azimah Abdul Samad, and her presentation titled Progress in Binary Zinc Oxide Heterojunction for Polluted Water Restoration. Please welcome.
Thank you. It's the chair session. Okay, hold on.
Hello?
Hello. Hello.
Am I audible?
Yeah, but Doctor, now we are moving to the next presenter. It's okay if you have any answer. You want to continue your answer, you can directly put in the chat box.
Yes, may I proceed or I have to stop here?
I think you have to stop here because because now we are moving to the next presenter, Doctor. Hello.
Okay.
Okay.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. I'm Nur Azima binti Abdul Samad. Will present my mini review on progress in binary zinc oxide heterojunction for polluted water restoration. Okay, in this mini review, I will I will tackle the issue on the water treatment techniques and also the utilizations of solar-driven nanostructured metal oxide, and what is the weakness of the metal oxide and how to overcome these weaknesses, and to study the mechanism of fine-tuning band gap. Okay, based on the Wendell Berry, from his quotes, he said that the earth is what we all have in common. The earth is our common ground. Therefore, we need to be very extra cautious in every action, in every of our actions. Okay, the significance of water for human being, animal, environment, and earth itself is definitely very important. Two-thirds of the earth itself is covered by the water, and 70% of the human body is made of water. Unfortunately, human activities is progressively polluting the water, and as a consequence, it produces the water pollution affects the human being, animals, and environment negatively. Okay, the water pollution cover the global warming water pollution, which is it is from the global warming problem, and also the atmospheric water pollution, mainly because of the air pollution, and the water pollution also come from the underground storage leakage, the oil pollution in water, and also from the nuclear waste dumping and the marine dumping. Also, the water pollution can be occurred due to the sewage and wastewater, and also from the domestic, industrial, commercial, and agricultural activities that generate wastewater. Okay, now we move on the alternative to treat these polluted or contaminated water. Basically, we have six methods to treat this polluted water, which are physicochemical. Physicochemical basically is the screening, the flotation, the sedimentation process, the coagulant process, the flocculant process, and filtration process. Meanwhile, the biological process to treat water, it is basically use the bacteria. It is less harmful to the environment with the fewer sludge, and it is also inexpensive. However, it needs large land area, and the process is quite high time consuming. Next, we have the chemical reaction, chemical route to treat the water, and we also have the physical route. Physical example is a membrane technology and also the absorption technique. And we also have the photocatalytic and electrochemical catalytic to treat the water. However, the selection of water treatment techniques is actually determined by the type of the contaminants found in water. Basically, if we see the water treatment plant, there are combinations of techniques to treat different pollutant. Okay. Now in my research, I choose the photocatalytic process or photocatalytic technique because it is quite it can be considered as AOP, the advanced oxidation process, and it is quite cheap, and also it is quite new technology. Okay, why the prime? Okay. For us to choose to do the photocatalytic activity, we need to choose the correct photocatalyst, which is it needs to have high photocatalytic activity. It also need to be a high reactive material, photo stability, and it must be chemical stability and biological stability. Okay, and in my study, I choose metal oxide materials. Why I choose metal oxide materials? Because it increased the oxidation process. Because to treat the water treatment, we need to increase the oxidation process and the mineralization process in water, in polluted water. And the common metal oxide is titanium, zinc oxide, MnO4, because this is quite abundant materials and quite cheap materials compared to other materials. And in my case, I narrow down to the zinc oxide materials. Why? Because zinc oxide, it has the properties of when it decrease in the size from micro to nano. Example, in micro zinc oxide, the band gap is very small, but we need a little bit a band gap there because in order to enhance the movement of the electrons. However, and the band gap is around 3.37 electron volt for zinc oxides. And also the zinc oxide has a quite good quantum confinement, which is the energy level is quite good. And also it is acceptable valence band and also conduction bands. Okay, other things that we need to consider zinc oxide for photocatalytic activity is it has polar surfaces. Besides that, zinc oxide also possesses 3 different crystal structure. Okay, with the it has cubic rock salt, cubic zinc blend, and also tetragonal hexagonal wurtzite structure. The wurtzite zinc oxide is very preferable because the coordination of a tetrahedron atom in zinc oxide lead to it will enhance the movement of the electron. Thus, it left behind holes that will increase the oxidation process. Okay, for the polar surfaces, zinc oxide, it has later I will show you in the next slide. It has many basal planes, which from one basal plane to another basal planes, the coordination or the arrangement of the atoms will increase the movement of the electron, and it produces spontaneous polarization throughout the z-axis, or we call it as the z-axis, the z-axis. Okay, this is the zinc oxide nanostructures. Another things that I choose zinc oxide because it has it is rich of zinc oxide nanostructures. Basically, this is from my project, but outside we have zinc oxide 1D, zinc oxide nanorod, zinc oxide nanotube, zinc oxide nanowire, zinc oxide nanoneedle, and for 2D we have zinc oxide nanodisc, okay, and also nanoplate, and also nanosheet. For the 3D, we have zinc oxide nanodendrite. We have zinc oxide nanoflower. Okay, and the single zinc oxide. This is what I call the basal plane. From one basal plane to another basal plane. Example, this is the zinc atom, and this one is the oxygen atom. So the electron from the zinc atom will jump to the oxygen, and it not jump to the zinc. It's just like our brain. We have many neurotransmitter where the electron in our brain jump from one neurotransmitter to another neurotransmitter just to increase the movement of the electron. Okay. Okay. However, zinc oxide, we have the as what I said before, it has a quite wide band gap, which is 3.37 electron volts, and I need to reduce it a bit to reduce the to increase the charge carrier movement, and also to reduce the charge recombination process. Okay, and also I want to absorb the photon. Because 3.37 electron volt only can absorb photon as energy under the UV light. Yes, we need UV light to treat the bacteria. However, if we can benefit the sunlight, it is more good. Okay. Okay. Therefore, I proceed with the band gap engineering. Okay, basically band gap engineering to diminish radiation-less transfer. Okay, zinc oxide has a quite low refractive index, which is the ability to absorb the photon is quite low. Therefore, we need a second material to help it to absorb the energy, and then we need to produce a new energy level or heterojunction. In my case, I produce another heterojunction to increase the performance of zinc oxide. And then I want to by band gap engineering, I also increase the interfacial electron transfer and reduce the recombination of charge carrier. Okay, this is the development of the zinc oxide. It's okay, I proceed because the time is okay. The time is very less, about 5 minutes. Okay, okay. This is after zinc oxide, we can incorporate it with the metal. Recently people incorporate with the titanium, the palladium, okay, in 2010s. But now, 2010 and above, people incorporated with another semiconductor or make it become tertiary. And this here, it is we combine it with another semiconductor, which is this is titanium, and this one is zinc oxide. Okay, this is heterojunction. If we combine it with the metal, basically it will produce another Fermi level in the band gap. However, in this case, we create the heterojunction. Example, if the electron here will jump to the conduction band after they receive the photon, then the electron will less recombine. However, it moved to another conduction band, thus it prolong the movement of the electron, and also it will leave holes that will accelerate the oxidation process. Okay. come to the conclusion, the incorporation of other elements in metal oxides, specifically in my case zinc oxide, will result in better separations of charge carrier, and also it will increase the lifespan of the charge carrier without by reducing its recombination rate. And also however, we must understand that we need an optimum concentration of second materials that only can improve the efficiency of the binary zinc oxide. If we exceed the certain concentration, it will show a poor performance also. And also the optimum concentration can help to reduce the band gap and absorb the radiation in case in like what I showed just now, titanium have the refractive index, which is quite high, so it able to absorb more photon, and also it will help to increase the interfacial from one phase to another phase charge transfer, and it will increase the photocatalytic performance. Thank you.
And thank you very much, Madam Nur Azimah, for addressing this interesting topic. Ladies and gentlemen, now open for Q&A.
Can I ask
Yeah,
questions? Dr. Hafiz? So I have a question. Did you compare the performance of the zinc oxide alone, titanium oxide alone, and also the heterojunction? What will be the performance of this heterojunction when you have together titanium oxide and zinc oxide?
I did compare with the titanium itself, zinc oxide, and also the combination heterojunction of titanium and zinc oxide. Okay, from what I can tell you that from the band gap itself, the titanium band gap around 3.2 electron volts, while the zinc oxide 3.37 electron volt. But after we combine it, it will produce 2.85. So it will improve the movement of the electron, and also from the photocatalytic activities, the percentage of degradation increase in heterojunction titanium zinc oxide as compared to the zinc oxide and also titanium itself.
Okay, that's all, Dr. Rika. Okay, now move to Dr. Aida. Salam Azima, why you choose zinc oxide in your research? The band gap is large, around 3.2 electron volt.
Okay, why I choose zinc oxide? Because it is an abundant materials we can see, and it is quite very cheap actually as compared to other material. Okay, before this I worked with titanium and tungsten oxide. It is tungsten oxide was very costly, and for titanium also. Therefore, I choose zinc oxide, and so we can. Besides that, also I choose zinc oxide because it is since I work with the water, so it is nano safety. I consider the nano safety there. Okay, it is non-toxic. Even we can find zinc oxide in our makeup. So it is for safety also, for the performance, the cost. That's why I choose the zinc oxide as compared to other materials.
Okay, thank you, Madam Azima.
Thank you.
Okay, now we are moving along to our next presenter. Please welcome Madam Nurul Fatimah Basir and her presentation entitled Development of New Organosulfur Extreme Pressure Additive for Metal Working Fluids. Please welcome.
Assalamualaikum and very good afternoon. My name is Nurul Fatimah and my presentation is about the development of new organosulfur extreme pressure additive for metalworking fluids. I've been supervised by Dr. Nadir Ghaffari Fadil, Dr. Yasmin Abdul Wahab, and Professor Dr. Muhammad Rafi bin Johan. So this is the outline for today's presentation, which focus on introduction, material and methodology, results and discussion, and lastly conclusion. So from the history chart, interest in metalworking fluid research has rapidly increased in the last decade. So many researchers generate and develop better additives for use in metalworking fluid. So holds same function as lubricant. Metalworking fluid is a name given to a range of oils and other liquids that are used to cool and lubricate metalwork pieces when they are being machined, ground, milled, and etc. So by the year 2000 until today, there is a strong regulatory push to replace short and mid-chain chlorinated paraffin, which are common and very effective extreme pressure additives due to health and environmental concerns. So the high demands of chlorine-free extreme pressure additives are due to material and energy saving, increased productivity, and improved quality of available additives. So there are two types of metalworking fluid with oil-based and water-based. So oil-based is mainly used in processes requiring efficient lubrication, while for water-based is used when heat dissipation is more necessary than lubrication. So there are various types of additives is added to metalworking fluid to enhance and accommodate the problem arise. So the benefit of metalworking fluid include carries away heat and contaminants while preventing damaging surface to surface contact, help in reducing corrosion, soot dispersion, acidic combustion, and testing on engine surfaces, and as well as reduce tear and wear by laying down a chemical film on surface. So for type of additives, there are active and non-active additives. The active additive chemically react with the metal surface to form a sacrificial film on it. And for non-active, the films mainly form by deposition of themselves or their byproduct. So example of active additive is compound containing sulfur, halogens or phosphorus, while for non-active is boron compound, silicon compound, aluminum compound, zinc compounds, and lead compound. So from the activation temperature of EP additive, it shows that metals that contain sulfide layer has highest activation temperature. Thus indicate that this sulfur additive is suitable to use in extreme pressure and temperature condition. So example of additive contain sulfur are sulfurized fatty acid, monosulfide, disulfide, tri or polysulfide, lithium carbamate, and lithium 1,2,3-tion. So aim of this research is synthesizing symmetrical and asymmetrical sulfide and disulfide as extreme pressure additive and as an alternative of current chlorinated paraffin, which can withstand high temperature and pressure, environmentally friendly, and also cost effective. So for material, we use Demacapto 1,3,4-tadazole as organic sulfur source. Because most of tadazole are insoluble in common base oil, so we need to add other functional group to enhance their oil solubility. So the advantages are low in price, available in market, and easy for storing and handling. So tadazole have three active sulfur in their backbone, and according to literature, the high sulfur content of tadazole and their derivatives provide multifunctional properties that allow it to perform as an extreme pressure agent, metal deactivator, metal passivator, or antioxidant. Also, tadazole can serve as an anti-corrosion and anti-rust agent. Based on literature, the tadazole ring is the key structure for inhibiting metal corrosion. Also, sulfur and nitrogen atoms hold certain load carrying and lubrication capacity. So for methodology, first we mix the tadazole with base and alkyl halide in reflux condition. Then we use TLC to monitoring the reaction progress, the production of major and minor products, and the optimization of the reaction time. Then we go for experimental workout to remove the solvent and unreacted material before purify the product. After we separate the product, we send the sample to NMR for structure confirmation. And lastly, for further analysis, we send the sample to GCMS for compound quantification. So for result discussion, from this reaction, there are two compound structure produced, which are monoalkylated cytosol and bisalkylated cytosol. So according to experimental entry here, there are 5 reactions done for this experiment with different parameters. All the entry has different after experimental workout. So we use different solvent to separate product and unreacted reactant and to determine the suitable eluent for column chromatography for the product purification. For alkyl halide, this time we are using chlorocyclopentane, while for the bases, we use different type of bases such as sodium methoxide, sodium hydroxide, and potassium carbonate to promote the green technology of producing monoalkylated and bisalkylated 1,3,4-cytosol. So from this, our analysis, it shows that entry 8 is suitable to use as optimization condition because of low toxicity of potassium carbonate and also lower in price than other 2 bases. Then with the ratio in step 1 and 2, we can get more yield and we observe a complete conversion of cytosol in step 1 with TLC. So this slide shows the 1H NMR for entry 6 until entry 9. So the 1H NMR is after column chromatography, show the structure of bisalkylated product. So both sides of alkylated cytosol have same hydrogen ratio, which is 1:4, as displayed by A, B, and C. So, however, different shifting of B is because of hydrogen appear in equatorial and axial direction. So, due to symmetrical and asymmetrical structure of alkylated cytosol, shows same HNMR. So, HNMR cannot differentiate between mono and bisalkylated product. So, the carbon NMR plays a main role to prove which compounds are isolated after column chromatography. So for carbon NMR, the result fit for the structure of this alkylated cytosol compound. We can see that the aliphatic side show 3 peaks of A, B, and C, which is the total number of carbon contained in the cyclopentane. For aromatic side, symmetrical sulfide 3S shows only low intensity of carbon at a peak D, while we expect to observe double intensity peak for cytosol carbon due to asymmetrical structure. Also for entry 9, there is a little bit different peak pattern, as you can see that there are 3 peaks at a D position. So this brings us into ongoing research. So this is the TLC for sample after being purified for the entry 9. So it only shows 1 peak. That means 1 compound is available. However, when we send the sample for NMR, it shows 3 peaks of carbon. So we expected that the peaks belong to the mixture of compound B and compound C, that both of the compound is undergoing aerobic oxidative coupling of compound A at a carbon number 2 and 5, thus then producing a symmetrical 5s. So, but then this probability needs to be double confirmed when we will be able to resume the network. For GCMS, the slide shows gas chromatogram of sample E8 after experimental workout. So for GC, we only take the peaks with torture area more than 5% into the calculation. So less than that will be considered as impurities. So from this GC chromatogram, torture area more than 5% is shown at retention time of 20.98 with 8.173% and with retention time of 26.60 minutes with a mass of 66.99%. So for the product structure is appeared by fragmentation as per next slide. So this slide shows the mass spectrum for this alkylated compound at retention time of 26.186 minutes with area of 60.85% and 26.598 minutes with area of 66.99%. So from both spectrum, it shows that two rotamers of this alkylated tadazole with total mass above 83% and no reactant is detected. Also, same fragment of MZ286 are observed at 219 and 218 and also Y51. So, all data prove that this alkylated tadazole exists in as two rotamers. As for conclusion, we can say that this experiment is inexpensive, can be done in one-pot reaction with eco-friendly medium that use ethanol as solvent under an inert atmosphere. Then this reaction is also free from foul-smelling TOs and require easy experimental workup. Then it is confirmed that this methodology produces bis alkylated tadazole as major product and monoalkylated tadazole as minor product. So this compound can be used as a main structure for the additive into naphthenic and paraffinic oil. For future work, first we will confirm the structure for E9. Then we will blend the produced compound with base oil and check its solubility with concentration not more than 10%. Next, we will use this additive with tribology test to examine the additive performance. As proposed by literature, two tests will be applied, which are four-ball and EP test for tribology study and copper corrosion test for corrosion monitoring. We will also synthesize symmetrical and symmetrical mono and disulfide with different cyclic and long-chain alpha halides using optimization condition of entry 8. So that's all. Thank you.
Thank you very much, Madam Nurul Fatimah Basir, for addressing this interesting topic. Ladies and gentlemen, now we come to Q&A session. Now
I would like to ask a question. Thank you, Madam Nurul Fatimah, for interesting topic. I would like to know, when you do the analysis of your products, you have two products, right? How do you measure the selectivity? That is first. And the second one, in the GCMS, I realize you also still have your reactant. You still have the peak of the reactant. So it means that you did not get the what is the percentage of the conversions in your reaction and how you compare that with the existing one, the existing catalyst. Is that favorable or not favorable?
When we analyze the GC, we found that
the conversion is about 88%.
80%.
Yeah.
How about the
And then-
selectivity?
because the tidazole itself, we have to control the ligand, the functional group. So we have to be cautious on the number of mole that we use, the what is it, the temperature of the reflux, because when we observe that when the temperature is go down or under ambient atmosphere without reflux, the color of the solution is different from the reflux. Yes.
Okay, thank you.
Okay. Any question? If not, I have one question. Okay. Corrosion is one of the problem for sulfur. Then how you deal with this matter? Because for the future you will run tribology test. But let's say in the future you want to produce one product. So how to deal with this matter?
Okay, in general, sulfur is corrosive when it turns to sulfide ions. So in organic chemistry, when we modify the chemical structure of its compound, it will change the chemical and physical properties of the compound. So in my case, I synthesize mercaptan compound to thioether compound, which has good anti-radical properties. So this thioether can act as secondary antioxidant that is frequently referred to as a hydroperoxide decomposer. So it act to convert hydroperoxide into non-radical, non-reactive and thermally stable product. So it will prevent the engine to become corrosive.
Okay, thank you. So any question? If no, okay, thank you very much, Madam Nurul Fatimah Basir. Okay, now we are moving along to our next presenter. Please welcome our invited speaker, Dr. Rika Rahman binti Nasaruddin, and her presentation entitled Enhancing Catalytic Properties of Ligands Protected Gold Nanocluster by Silver Doping. Please welcome her.
Okay. So, Assalamualaikum warahmatullahi wabarakatuh and a very good evening to you all. So today I'm going to present to you, this is actually a part, I think this is the last objective number 4 of my previous PhD study, which I continue the study when I reported my duty as assistant professor at IIUM. So, and as you can see the title here, I'm working on enhancing the catalytic properties of ligand protected gold nanoclusters by silver doping. So this study, me as the doer of the experiments, and also I have a colleague, Dr. Max, okay, already graduated his PhD. He is now at Green Catalysis Research Group at NUS, and Prof. Shea Jumping was my supervisor for this project. So before that, I would like to just briefly tell you about what is this ligand protected this one gold nanocluster. So as compared to the single atom and also nanocrystal, nanoparticles, nanocluster is in between them. So nanocluster, it has smaller size, which is less than 2 nanometer, and some reported study, they mentioned the size is less than 3 nanometer. So in terms of number of gold atoms, it going to have about 10 to 150 gold atoms, and it is highly monodispersed. It has unique atomic packing structure, which I'm going to share to you later. And then because the size is too small, so it reached this quantum confinement effect. So it behaves like molecule. It has discrete electronic structure. So if you look at this UV-vis electron spectroscopy, the results
the absorbance, you can see it has these several peaks. Okay, so like this one, this peak at 670 nanometer belongs to the core, and this one at 450 nanometer, this one belongs to the shell structure. So it has also homo-lumo electronic transition as compared to nanoparticle, which have semi or continuous electronic structure. So if you look into the color is also different. The color is like brown, bright brown. However, if you go for gold nanoparticle, the color is ruby red. So this is another unique things about this ligand protected gold nanocluster, which you can produce it with atomic precision. What does it mean? It means you can know the number of the gold atom, and also you can know the number of the ligands. And then it also has this unique well-defined structure. For example, the most famous gold ligand protected gold nanocluster is gold 25 with 18 ligand. So it has these 13 gold atoms in icosahedral core and protected by 6 dimers. So the 6 dimers, it has 2 gold atoms with 3 ligands. So, and this is an example of the structure which I produced using molecular dynamic simulation with charm function. And another thing, there are several types of ligands that can be used to produce this ligand-protected gold nanocluster. But the most famous one is tyrolate, and because why? Tyrolate, it can have this strong gold 1 to sulfur bond. So that is why usually, as compared to gold nanoparticle, we will say that the ligand protected on the gold atom by covalent bonding as compared to common van der Waals interaction. And not only that, because it has this atomic precision, so what happens if you are going to, you are going to identify what are the species of your metal nanocluster, like gold nanocluster, you can do ESI-MS analysis. So you can do some simulation with the isotope pattern, and you can identify what is the species. For example, like this one, Au25, okay, all of this also Au25, but this one with 6- charge, okay. So it is a well matched, so you know that your sample has high purity of Au25. So why we would like to study this gold nanocluster for catalysis? So if you look into the size is smaller as compared to the common gold nanoparticle. So as the smaller the size, the more reactive the particle. And then when the more reactive the particle, not only that, they also have higher surface area. Thus, they will have a higher reactivity or higher catalytic activity. So if you look here based on this TEM, okay, like this one is 10 nanometer, you can see that the size, this is gold nanoparticle. Okay, the size is more than 2 nanometer. Like this one, this is what you are going to see if you try to view this gold nanocluster under TEM. You can see it is look like a circle, but actually it's like, you can see like dot of atom like try to connect to each other. So it's more like I call it like a flower, or not a flower lah, tapi if you go down in deeper, you can see like there are a lot of dots in this one circle. So this is what usually you can see when you try to view gold nanocluster under TEM. And this is the common gold nanoparticle. And if you look carefully, the differences between particle and also cluster, like this one, you can have high monodisphersity, but this one you can have different size. Like this one, if you stabilize it using polyvinyl pyrrolidone, you can have different size. So to get a better monodispersions of nanoparticle, if you try to get atomic precision, you can have a better monodispersion. So in terms of the accomplishments of gold nanocluster for catalysis, there are several chemical reactions like published in this coordination chemistry review. So you can do oxidations, we can do hydrogenations, we can do coupling reactions, and also electrocatalysis. So another important features of this ligand protected gold nanocluster is it can behave like, homogeneous gold nanocluster catalyst. It is like quasi-homogeneous gold nanocluster catalyst, which you will have this active gold. Like this one, the core is going to be your active gold. Like in homogeneous, you will have this atom, okay, gold atom, and complex with the ligand. But this one, you will have a staple motif as the protecting shell. And then you also have the ligand. Not only that, if you are going to do the immobilizations and you remove your ligands, you can have a smaller catalyst on the support material. And as I mentioned before, the smaller the catalyst, the higher the surface area and the more reactive the catalyst for catalytic reaction. And then another thing which is good features of this gold nanocluster ligand protected, what you can do is you can also study the important roles of the ligands. For example, with the ligands, you change the ligand, you do something to the ligand, you add, okay, more ligand, not only one ligand, you can have bi-ligands. So you will do something, or you can understand the effects of this ligand to the synthesis process. And not only that, the ligands can also affect the physicochemical properties of your gold nanocluster for like this one, in terms of the chirality, in terms of the electronic structure, photoluminescent properties, and also for biological activity. So it can be used to actually tailor your gold nanocluster for your specific reaction ataupun your specific application. And then in catalysis, usually the ligand, you can learn even more and deeper on how the ligand modulate the active sites, the reaction pathway, and also the selectivity, and how the ligand can control the catalytic activity and accessibility, and how the ligand can actually facilitate the absorptions of this gold nanocluster on the support. And for my particular gold nanocluster, the one of the uniqueness is also we produce it using water. So it is a green soluble water soluble gold nanocluster produced using water as the solvent. So it is greener as compared to those produced using organic solvent. So these are basically the overall study of this ligand protected gold nanocluster. Previously, we focused more on this benefiting the ligands, all right, the effects of the ligands to landscape, to the accessibility and catalytic activity of this gold nanocluster, the roles of the ligands to the active sites of gold nanocluster and the reaction pathway, and then how actually the ligands behave and then during the catalytic reaction, and how the behavior of this ligand actually cause the structural transformations of this gold nanocluster during catalytic reactions. And today, I would like to focus more on this metal composition. So this is like a metal engineering, how you can actually tailor the performance, the physicochemical properties, and the activity of this gold nanocluster by having silver doping. So this is the scope of the study and the methodology. So we are focusing on this gold 25. So it means that we are producing this metal 25 metal nanocluster. It means that in one particular nanocluster, you will just have 25 metal. And the method that we use sodium hydroxide mediated sodium borohydride reduction method. And the ligand for this particular study is C6 mercaptohexanoic acid. And we use co-reduction method for both silver and also gold precursor. So for the purification, we did centrifugations, and also we use this PD10 column to purify the bimetallic the gold nanocluster doped with silver. And then these are the analysis that we did. So for the model reaction, we just selected a simple reaction which is quite easy to use and quite easy to make and quite easy to analyze. Okay, you can look at the behavior of the reaction. So this is just for nitrophenol hydrogenation in solution, which you can have time evolution UVVs in order to see how long it will take for the reaction to complete. And also you can find the induction time for the accessibility and also apparent reaction rate constant by using this kinetic mode of UVVs analysis. So for the results, so these are the characterizations of the catalyst. So if you look here carefully, this is only gold. So you will have the characteristic peaks of this gold 25 nanocluster. You have peak at 670 nanometer. You also have peak here at 450 nanometer. So this is gold 25. But when you try to add this silver, okay, like this one with this ratio 24:1, you can realize that you will get changes. Okay, you will get changes in the peak, especially at this 670. And then when you add more silver dopants, okay, you can see that this appearance of the peak at 670. And later on, when you get higher, you get even more the peak disappear, and then you have one peak here. So if you try to add more, you may not get, okay, let me just show you later. Okay, what happened if you try to add even more silver, you cannot get a nice ESIMS. So what is the role of this ESIMS? Okay, this is the analysis by ESIMS, electrospray ionization spectroscopy. So you can identify the number of gold atom, the number of silver atom in the solution. For example, like this one, when you try to use this ratio, feeding ratio, what you obtain, you can have gold, okay, with the range of 18 to 21. And if the gold is 18, the silver is 7. So it means that overall, the total number of atom, the metal atom in your species is still 25, right? So this is the how you identify, you realize that, how I identified. So we match the ESIMS peak with the simulated isotope. So this is an example, evidence of one of the species inside this solution. So this is what, okay, so based on this characterization, we successfully produced bimetallic Au25 minus X and silver X. Okay, MHA is the ligand, actin ligand with 25 metal nanocluster species. So if all of these have 25 metal nanocluster species, it is assumed that they also have similar structure that I have that I already showed to you before. So these are examples that what I mentioned just now. If I try to increase more, like this one, I try to increase the ratio, okay, and I try to produce silver 25 nanocluster using MHA as the ligand and using that particular reaction condition, all right, I can still have the cluster, but it is very difficult to identify them using ESI mass spectra. Why? Because this, when you add more silver to the cluster, what happened? It is unstable under ESI mass analysis. So then what we did this oxidation state SPS analysis in order to know the oxidation state of the gold. Okay, so this is the example of each of them, and we also performed the convoluted XPS spectra in order to identify what are the species of gold inside this gold nanocluster. So as you can see, we have these higher amounts of gold 1 as compared to gold 0. This is example for this Au2025. Right. So I will explain more about this later with a table so that you can understand better. So now, based on this one, when we increase, okay, the silver, okay, we can realize, all right, if you check here, there will be more of Au1. Okay, electrons are used to reduce Ag1 or AgSr complex. So this is the oxidation state for silver dopants. So here, this is the example of the convoluted SPS spectra. So from here, you can also see here, it is quite different. When we add more of the silver, we see more silver 0 as compared to silver 1. So what does it mean? Okay, the presence of higher silver 0 indicating that the silver dopants do not prefer staple motif location. So let me just briefly explain to you what happened. This is the what we call the magic structure of Au25. So you have the core here. Okay, so usually inside the core, okay, the structure of this, the oxidation state of this metal is 0. However, at the staple motif, the oxidation state of the metal is 1. So when we observe, okay, the results, okay, the percentage of gold 0, gold 1, silver 0, and silver 1, we start to realize that actually, okay, if we would like to hypothesize, if the silver dopant preferred the location at the staple motif, we should have higher silver 1. However, the silver dopants that we obtain, okay, from the SPS analysis, most of them are silver 0. So it means that these silver dopants, they prefer the location at the vertex of this gold core, okay, at the vertex. So they just replace the gold at the vertex of this core. So that is the possible solution locations of this XPS. So just return back to this XPS UVB spectroscopy, you see it here carefully that the peak at 670 disappear faster as compared to the peak at 450. So the reason here, it shows that the disturbance occur at the core rather than at the staple motif. So UVVs also support our justification. Then we do the catalytic analysis. So when we perform the catalytic analysis, we realize that when we increase the silver dopants, it also increases the accessibility, even though we have similar types of ligands. And it also increases the catalytic activity. Okay, as you can see, the induction time, when the induction time decrease, it means that it has higher accessibility because it takes a shorter time, okay, to perform the catalytic activity. And the apparent reaction rate constant increase means it has higher catalytic activity. Right? So, how this catalytic enhancement occurred by this silver doping? So, based on our analysis, we believe it is because of combinations of several factors. So, one of the factors is, of course, it is the synergistic effects between the gold and also the silver. So, what we found based on our literature review, the silver dopant actually increased the HOMO-LUMO gap energy. And the second reason is because of the weaker silver and sulfur bonding as compared to gold and sulfur bond. So when we try to replace the gold with silver, so we have weaker bonding between the silver and also the ligand. So you try to imagine the reaction when we remove the ligand, so we open the active sites more to the reactants. That is why the catalytic activity increase. And this one, we also realize there is also weaker silver hydride bond than gold hydride bond. So what happens if it is weaker? So it means that it will be easy to do the catalytic activity. Hydride, okay, based on our previous study, okay, I will show you later, but this is the DFT analysis to confirm the weak interaction between the gold to the sulfur, gold, and silver to the sulfur. So if you look here carefully, when we add, okay, this is before we add hydride. So the removal of the ligand is not that easy. Okay, the energy need to remove the ligand is quite hard. It's about 500. But still, when we add the silver, the energy reduced a little bit. Then when we have hydride, as you can see, the energy also decrease. So it means that the presence of silver actually improve the removal of the ligand. And also, as mentioned previously, due to the weak interaction between the silver and also the hydride, so the catalytic activity can be done faster. So this is example of previous study that mentioned removal of ligand is very important in order to activate this gold nanocluster catalyst. And we also performed this study in order to understand the effects of ligands removal to the catalytic activity and also the structural transformation. And what we realized, when the hydrides bonded to this atom, so it opened more of the active sites to the reactants. And because of that, we can have higher catalytic activity. And the fourth reason is, okay, this one we try to identify, is it really the cluster as the main active species during the catalytic reaction? So what we did, we compared the performance of this metal nanocluster with metal MHA complex. So like this one, we did not reduce this mixture. What happened, we just add the metal precursor and also the ligands with the same amount, and then we did not add sodium borohydride, so we just have metal ligands complex. And then here we just check the activity of the mixture of metal precursor. So what we realized, the activity of metal nanocluster is far higher. So it means that the main active species is actually the nanocluster, not the complex, not the metal precursor. And then the last reason is because the gold nanocluster, gold silver nanocluster is more stable in the catalytic environment. So the stable here means that it is stable in a small size. So if you look here carefully, when we add sodium borohydride, okay, to this gold 25, after sometimes we have peak at 518, and this is actually a peak of gold nanoparticle. So after sometimes what happened, the size of this gold nanocluster it start to open the ligands, and then it do some restructuring of the structure, and it becomes higher, bigger gold nanoparticle. But when we add the silver dopant, after some time we can still have a smaller nanoparticles. That is why the activity is higher and better. So this is the conclusion for the study, and the manuscript is already submitted to nanoscale. So we realized that we can increase and enhance the accessibility and catalytic activity of gold nanocluster by silver dopant without compromising the presence of ligands and also the atomic precisions of the gold nanocluster. So it means that the metal nanocluster. So thank you for your kind attention. I would like to acknowledge International Islamic University Malaysia for the study, National University of Singapore, Ministry of Higher Education Singapore, and Ministry of Higher Education Malaysia. This is my contact information, and this is just the TOC of the study. So that's all. Thank you.
Yeah, thank you very much, Dr. Rika, for addressing this interesting topic. Ladies and gentlemen,
Dah dapat kira tak? Dah dapat kira? Dia dah keluar dah dekat Excel.
ladies and gentlemen, now we come to Q&A session. Okay. So, is there any question from the floor? Okay, Dr. Rika, I have one question. Okay, actually for nanoparticles, sometimes we have a problem on stability. Then how to overcome these problems?
Actually, it's not only nanoparticle, nanocluster also has problem in terms of stability. So at the end of the day, we still need to do some, either you do the correction in nanocarrier, you have nanoreactor to do the reaction. So whatever it is, even though it is unstable or even though it has this structural transformation, it is still inside that. So when the final fit will be within the expected size. Okay, and that is the other one solution. The famous solution is actually you have to support your nanoparticle onto a support material and make it heterogeneous. Now that is the common method lah. And the recent one is to have nanoreactor.
So anyone?
Assalamualaikum,
thank
Doctor
you.
Azim. Okay, I have one question. I know whether your material is suitable to work for photocatalytic activity or
Yes, can,
photochemical
because we
reaction?
have silver kan, silver ni semiconductor. But in order to do that, because this one size is too small, so I did not perform the study on the photocatalysis, but I do believe it can, because some others already did.
I'm sorry, what is the size?
This one is
of
about
your
1.5
material?
nanometer, too small.
It suffer tak awak ni gumpalan?
Agglomeration.
Agglomeration.
Agglomeration, okay, because it has this 18 ligands kan. Okay, it depends on the ligand that you use. If you use ligand with like p-mercaptobenzoic acid with this benzene ring, the structure is more stable in solution after some times. But during the catalytic reaction, without any support material, they will have some structural transformation. So you at the end of the reaction, you may not get again your Au25, for example. You can get a bit bigger. For example, in my previous study, after the catalytic reaction, we get Au26.
Oh, is it possible if I combine this material, example, with my zinc oxide, titanium oxide?
Yes. Usually what we do, it is as electron mediator.
Okay.
It will do some enhancement. Like photosensitizer. In cancer therapy, we use gold nanocluster as photosensitizer. It can mediate the transfer of electron because it is small kan, so you can just decorate your punya catalyst with this one.
Okay, thank you so much, Doctor.
Okay, most welcome.
Okay, doctor. Just one more question. Other than catalytic application, is that possible if you use your nano cluster for a biomedical area, especially for antibacterial, because we know that silver is very good for as a antibacterial.
Actually, I am quite demotivated when Prof. Jackie mentioned don't use metal nanoparticle as the antimicrobial agent. That is what I'm working now. What I realized when I use gold and silver, due to the synergistic effect, the antimicrobial activity is better as compared to the silver alone and also gold alone. Gold, of course lah, we don't know much kan that they can have this antimicrobial property. But silver, we know it has this microbial property. When I add gold, it enhances the antimicrobial property as compared to this silver alone. But when I heard Prof. Jackie mention the activity is not as better as ethanol, that is true. That is true because our control antimicrobial agent we use, I forgot the name, but the common antimicrobial agent that you use for kids kan, pusat tu, untuk cuci pusat tu. So cyclohextridine, I forgot the name, sorry. That one is still far better as compared to metal nanoparticles. So I believe if you would like to do antimicrobial agent using inorganic nanomaterials, try to involve the organic antimicrobial agent as well. Put it as, you know, you decorate your cluster or your nanoparticle with that organic molecule. So that can reduce the nanotoxicity first. Second, improve the dispersion of your antimicrobial agent. This organic molecule can help to actually spread this antimicrobial agent to the bacteria cells. This is the study done by my colleague. And the third one, the toxicity effect will be reduced lah.
Okay. So any question from the floor? If no question, I would like to say thank you very much to Dr. Rika.
Okay, most welcome.
Okay, now we reach at the end of this session. Before that, I want to announce the best presenter for this session. And the best presenter for advanced nanomaterials for catalysis session goes to Madam Nurul Fatimah Bakir. Congratulations, Madam Nurul.
Congratulations, Madam Fatimah.
Congratulations, Fatimah.
Okay, thank you very much to all presenters for your participation. On behalf of the MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill up the feedback form as given by session moderator in the chat box. You are invited to join the rest of the event. Hope to see you again. Thank you very much.
Thank you, everyone. Nurul Azima, if you would like to test my sample, just let me know.
Sure.
I can supply it to you directly if you would like to test it. Okay.
Thank you, Doctor.
You're most welcome. Thank you, Doctor. You're most welcome. Congratulations, Fatimah. So we can leave now, right?
Yeah.
Or there is something dekat stage. Oh, networking. Okay. All right.
Okay. Thank you very much all.